Sand grain segregation has been the subject of countless technical articles, research papers, video presentations, and discussions among foundrymen. Despite all this attention, it remains a primary cause of problems and a leading source of inconsistencies in the sand casting process. These inconsistencies can result in a myriad of defects, as well as the additional expense of high resin consumption. This video will demonstrate why sand segregation cannot be prevented and why reblending at the final point of use is required. It shows how sand grain sizes segregate each time sand is handled and a practical method of reblending the sand at the critical point when the mold or core is made. The test sand used in this video is a round grain 55 AFS 4-screen sand with the screen distribution shown here. To demonstrate the effects of grain segregation, all of the sand on the 50 screen and coarser is dyed black, and all of the finer sized is left white. 40% of the sand is therefore black, and 60% is white, as shown in the beaker pictured here. To demonstrate how quickly segregation takes place each time the sand is handled, a quantity of the test sand is mixed thoroughly in a small container. The mixed sand is poured on a glass surface. As you can see, even this small amount of sand segregates by grain size with minimum handling. The larger grains roll to the outside of the pile, leaving the fines on the bottom and in the middle of the pile. Next, we simulated the transportation of sand on a moving belt. The sand is poured from a moving container onto a plate of glass, which also has a mirror to observe the underside of the would-be belt. The sand again segregates, the coarse on the top and outside edges, while the finer material is in the middle and bottom. These simulations indicate that maximum care should be exercised in the taking and preparation of samples for testing. They also demonstrate that no matter how well the sand is mixed at its source, when it's transported to the railroad car or truck, it segregates. For the next test, a miniature bin has been fabricated from plexiglass to simulate a foundry sand bin with a common top fill and bottom cone discharge. The bin has no anti-segregation devices. A sufficient quantity of the mixed sand was introduced into the bin to duplicate the normal flow in the foundry. Again, the sand segregates immediately within the bin, the fine staying in the middle while the coarse rolls to the outside. The outside of the bin shows almost all black material or coarse sand, although only 40% of the total sand is black. This drawing illustrates what occurs within the bin. The center core, depicted by red, is a concentration of the finer screens. The pink area contains a blend of coarse, fine, and intermediate grains, and the white area contains the coarser grains. As the bin unloads through the bottom center gate, the center core of fine sand immediately exits, forming a funnel-like opening down the middle of the bin. This phenomenon, known as rat holing, can be seen as the center dome of sand collapses into the center of the bin as it empties. After the fine sand is gone, coarse sand falls into the funnel and discharges rapidly. This results in a wide variation in the screen distribution of the sand exiting the bin. Variations from an AFS number of 46 to 66 were experienced with the 55 AFS test sand. A plexiglass model of a railroad car was also fabricated, and similar loading tests accomplished as shown here. The results were the same as the round bin results. The fines were concentrated in the middle and at the bottom, with the coarse material rolling to the outside. Again, this illustrates the importance of proper testing procedures when testing the sand from railroad cars or trucks. This shows a simple siphon rigged to extract the sand from the center of the bin. As you can see, the material is very white without any trace of coarse grains. Shown here are plastic models of two sand reblending devices that are very effective as the sand exits the bin. First, to the right of the picture, is a bottom device referred to as an inverted cone. The cone has four half-circle openings located at equal distances around the circumference of the base of the cone. It's critical that the total area of these openings is less than the total area of the bin discharge opening. That way, sand flowing through these openings will exit without backing up and filling the chamber under the cone. The second device is a bin loading diffuser that distributes the sand to four locations in the bin. Here is the inverted cone placed at the bottom of the bin. Because the method of filling the bin has not changed, the sand segregates as seen in the previous tests. That is, the fines are in the middle and the coarse grains roll to the outside. The bottom gate is now opened and the sand exits the bin. The sand dome formed in the center of the bin does not immediately fold in. Instead, it rides down on top of the sand. This indicates the sand is feeding through all four openings in the inverted cone and going down level. The arrows on this illustration indicate how the sand is feeding to these openings in the inverted cone. The coarse grains on the outside are blending with the fine grains on the inside, as well as the intermediate grains which are halfway across the radius of the bin and exiting through the openings in the inverted cone. Since the area of discharge is larger than the sum of the four openings in the cone, the sand is mixed together at the discharge. With the insertion of the inverted cone reblending device, the AFS number of the sand discharged from the bin was held to a range of plus or minus 3 points. When the sand diffuser device is installed at the top of the bin, along with the inverted cone at the bottom, reblending efficiency is further enhanced. Although sand still segregates as the bin is being filled, the pattern of segregation is completely changed. This can be seen by observing the outside of the bin. The sand is now divided into four compartments located above the four openings in the inverted cone. Each compartment is reblended through the inverted cone openings and the bin discharge. Viewing at the bottom of the bin as it empties illustrates reblending occurs even at the very bottom of the bin. Using both of these devices in a sand bin further enhances the reblending. Tests have shown the sand will be maintained in a range of plus or minus 2 points variance in AFS number. Let us emphasize again, gathering of sand samples for testing must be accomplished meticulously. Whenever possible, reduce the sample to test size by the use of a sand splitter. The splitter ensures that all grains in the large sample are present in the smaller size sample and will result in accurate tests. It should be the foundryman's desire to eliminate variables in the casting process at every production stage. Sand is involved in many of these stages, and every effort should be made to ensure its consistency. Maintaining its size distribution is a major consideration in its performance. This cannot be controlled unless careful consideration is given to delivering a specified grain distribution to the mold and core producing stations.
For additional information or assistance, contact your U.S. Silica representative.